And then me and advice. Me and advice. I'm ready there. Can I go first? Yeah.
Can you hear me, Paul?
Yes, I can hear you fine. Thank you.
Oh, okay. Yeah, I
So
wasn't hearing anything. Thought it
I
was going to be
know
one of
this.
those meetings.
Yeah, well, this is going to be a very strange meeting because I'm not in Denver. I'm in
Oh,
Houston tonight.
oh, what you got going on down there?
Well, I figured I'd grab one of these rockets to the moon.
Yeah, well,
I'm down here, see if I can hitch
send,
a
send,
ride.
send us a postcard, will you?
Yeah, I'll talk to the guys at Lockheed Martin and NASA, see what they say.
Yeah,
Anyway,
well, you can recruit some membership down there while you're there.
yeah, it's true. That's true.
Yeah.
Lots of that around here. Yeah, so this is the first time I've done this. So guys, I really can't guarantee anything's going to work, but I'm using my single laptop. It's a small screen. Okay. I don't have my four screens, so I feel naked. And
Well,
and I'm in a house that my daughter and son-in-law and my three grandsons are here, along with
oh.
my SYL. And the place just reverberates everywhere. So I'm going to try to mute as much as I possibly can so that you can hear what's going on. But
Oh, we all have families. We know how that goes.
yeah, well, this is a trip down here. I'm going to be down here for 10 days while my daughter's traveling. So we're going to be babysitting the boys.
Oh, there you go.
Yeah, going to try to make hams out of these guys. I got a pair of twins, which are 8, and I don't know which one's which. And I got a one that's 10. So I'm in real trouble, guys.
Well, we had like twins in my high school class that you couldn't tell them even in high school. So we just call them twin. Mm, mm.
Well, it's it's yeah, they actually did the switcheroo thing, with their teachers in different classes, and they fooled everybody for at least half a day. But
Yeah. Well, wait until they get to the girlfriend age.
yeah, I don't want to even think about that. Yeah.
Uh,
So
uh, uh,
okay,
well,
so
you're coming in loud and clear here.
all right, thank you very much. I'm glad we're working out here. We got let's see, folks we got on here. Hey, there's Roger. Hey, Roger. Let me just see. I'm trying to. Oh, we got 17 participants right now. And see how this is going to work. You got Myron in there with the picture of the Earth from space, and say good morning or good evening to Myron. And I got Rob from Utah. Am I got the right state now?
No, Idaho.
Idaho. See, I knew I'd look. It was up there somewhere. It's the elevation. I'm too low.
Yeah. Yeah.
And there's Ted. Hi. Hi, Ted. I like your antennas in your background. I'm going to talk about those a little later. Maybe you can give us a few hints and tips on those. We've got Mark and
Morning.
yeah, Mark Drayton. There's a Mark G. I don't know who Mark G is. So if Mark G is there, you can introduce yourself. I'm not sure who you are. And there's Vlad, that really nice, handsome guy that was in the picture that we sent out from the EME contest. Hi, Vlad.
Good
And we
evening. Good evening to everybody.
Good evening, Vlad. And we've got Derek. Hey, Derek. Long time no see. And
24 hours.
and there's Martha. Thank you very much for coming on board, Martha. Larry, you're looking good. You got the patch on? No? Oh, okay. Looking for the parrot.
Yeah,
And-
exactly. I'm looking for the parrot.
Yeah. And Don, how you doing up there in Montana? At least I got that state right.
Staying with it.
Yeah, yeah. And
It's as they say, it's bucking hard, but I'm still on.
yeah, yeah. Yeah, I'll say good evening to my great friend Myron there, KL7YY. I don't know if he's muted.
I'm here.
Hey, good to hear you on there, Myron. I think you got two instances on here, but maybe I got it mixed up. I don't know.
I got two laptops.
Oh, okay.
My
Okay,
new laptop, trying to get a video working on my new laptop, and it's not working.
I see. Okay, well, one of them needs to be muted because I can hear a little echo. And good evening to Chuck N0NHJ from Glenwood Springs, and Kathy, and Rick. Yeah, folks from, let me think, Kansas, I think.
Oklahoma.
Oklahoma. All right. Geez, I'm doing bad tonight. Thanks, Myron, for helping me. And then we got Alex, K6VHF. This is big thumbs up. And we have Bill Miller tonight. And did I miss anybody? Because I got a small screen, so I might have missed somebody. If I did, oh, there's Dayton. Hi, Dayton.
Good evening.
Yeah, good evening, Dayton. Good to see you there. Let's see. And we got Fred Brandeberry. And let me think here. Because the screen seems to be changing around as more people are added, but that's okay. Okay, so let's see if I can find the agenda for tonight. See if I can make this work. Let me just let's see here. See if I can share something here. Here's the share button. And all right, which one do I want? Boy, okay, let's try this one. See if this works. No, it's not going to do anything. Come on, Paul. You know how to make this work. Let's see. You know, this was working earlier, but it's not working now. Let's see. Share. Okay, I don't know what you guys are seeing at this point. Oh, I meant there's a slide presentation. Whoops. One more. Someone coming up. No, that's not going to work. You
So
know,
do we have
There you got
Gmail
it.
coming up?
There it is.
all right. Well, is that the Gmail you're looking at?
Yep.
Yep.
Yeah, I didn't want to show that. I want. Hey man, let me see one more. Oh, here it is. I found it over here on this other. That's the trouble when you're dealing with a small screen. When you got a whole bunch of other ones. Okay, let's go to the slideshow here. And can you guys see a slideshow coming up?
I
Maybe?
think it's thinking about it.
Oh, good. All right. I hate these things. I wish I had an Apple machine here now. I'm getting
I was just getting ready to comment. You guys and your
Yeah.
Microsoft.
Yeah, I know. I wish I hadn't
You
been
know,
through this.
Paul's problem is he's just used to working with too many screens, right?
Yeah.
Too
You're
many
right.
large screens here.
Right. That's my problem. I got too many screens. So
Too many large
Oh,
screens.
we're back to Gmail.
I know I'm going to get rid of the Gmail here. So stand by here. Let me see if I can get rid of that. Okay. Now we're back to this one, which should be hopefully the screen that shows the slideshow. No,
Yeah, that's a slideshow. That's the
Okay.
pictures.
Please work. Hey, now we got a DSES engineering meeting.
There you go.
You can see it? Okay,
Yeah.
good. All right, now we're moving. All right, so thank you very much for everybody coming on tonight, and apologize if I've missed anybody. This is the Deep Space Exploration Society engineering meeting for December the 8th. This will be the last meeting of this year. So tonight, we've got on the agenda tonight, we've got the DSN or Deep Space Network, the installation results that Alex was working on over the weekend. We have some recent dish equipment that we acquired, and we also talk a little bit about the October EME contest and some new software that Alex has been working on, and a site report from Bill Miller if he has something new to report. So, wondering, Alex, are you ready to talk a little bit about the DSN installation and the stuff you've been working on? I shared a video of you explaining some of the way the optimizer was working for the feed, and maybe you can talk a little bit about that too. So, hand it over. Okay, I'm going to stop.
Yeah. You hear me okay?
Yep.
No.
Yeah.
A lot of noise on you.
A noise?
Yeah.
Yeah, I have a system running here that I was going to demonstrate. So.
That works.
Yeah, I guess the microphone has auto gain something. Probably. Alright, I wish I had a nice presentation like I always do. But unfortunately, I had no time. So, I'm just gonna share what I've got. Alright. You see it?
Yep.
Alright, and Roger, you might have more photos than me for the feed. Do you have them?
Not in an accessible form.
Okay. I thought I had, and you sent it to me, but I could not find it.
While we're doing this, I'll try to dig up a few.
Alright, yeah. So, this is photo from sunset on the Friday when we arrived. I posted plan what we're gonna do, but I don't have it with me right now. It's posted on DSES group. So I delivered the system last time when I was there back in October during the contest. So this is how the system looks. It's basically the RF module on the left side with the feed. The underneath is just a plate with a motor that we can adjust back and forth, about 10-inch total length of the actuator that goes on the Rogers mount. That's going to be next, and we temporarily kind of assembled the holder that holds the stuff, which is the processing module. It's the first generation of the module. Runs on Raspberry Pi. It has a separate controller there, the fiber optic converter, everything we need, and the power supply.
Hey, Alex, could you define what the DSN is for some who may not be aware of what we're doing?
Well, I was going to do that, but my assumption was that people are aware about the DSN because I posted so many information on the group's IO and everyone has access to it. So if anyone want to take a look and read through, we have a nice presentations and we have recordings from YouTube, and also we have a dedicated page. And I was talking about that last time. So there is a page on our website, DSES.science. Please take a time, and while I'm talking, you can go there and open up and look through. So DSN is a deep space network, and we had idea to have our own system at Haswell that allow us to receive signals from the deep space probes. This particular system operates on 8 gigahertz, but DSN also operates on 2 gigahertz, but we focus on 8 gigahertz because our main goal is to capture the signal, detect the signal from Voyager 1. That's the furthest man-made probe that humans built, and is currently flying almost 1 light hour away from the Earth. And I talk about this numerous times, but this time it's just update. Once again, I didn't have the time to make a nice presentation, but does anyone has a question at this point? That any question about the DSN itself? No. All right. This is the mount that Roger designed to feed the system, the RF module, with the motor assembly. So right now you see the motor assembly attached to that mount. The idea was initially requirements that we need to have flexibility to adjust the assembly up and down on actually X and Y Z's and also Z axis. So he made it such a way so we can actually move and slide the assembly until we get to a desired position. So the whole thing it's been designed just because to help us to understand what the focal point is. Before that, we just rely on the calculations. We know what's the diameter of the dish. We know what's the depth of the dish, so we can calculate the forward FD ratio. As well, we can calculate the focal point. And then we estimated that this is the point in the air. That would be the focal point. But we never actually truly verified if this is the focal point. So the idea was not just a DSN, but because the feed itself is so small and very light, and it's easy to move this feed assembly back and forth to try to find out is there a focal point misalignment, or we might find something else. So that was the idea also behind the DSN effort to do that. So the mount allows us to slightly adjust the location of the whole assembly. So this is the bench where I was doing some upgrades and testing. Last minute I decided to upgrade the system using the new module that I also posted recently on DSES, which is DCPM module that has a lot more powerful processor and the system itself. So because the old one kind of was lagging because you can't run a lot of, it doesn't have a lot of memory, and the processor is not quite powerful enough. And when you kind of run the Python codes on it, besides the Linux itself, it's kind of making everything inefficient. So I had the time and I decided to upgrade. This is the test bench where I'm programming and field testing the new system. This is the whole test bench looked like where we were doing some adjustments. Roger installed feed mount on Saturday morning. We want to do that on Friday, but we ran out of time and it was pretty cold, and working in the dark and cold kind of wasn't our desired way. So we decided to do on Saturday. So we did, and I tried to receive the signal, but I ran a problem because there was no sources, no any reasonable signal sources, because in order to test something you have to have something in the space. So I tried to use manual tracking system to slew the antenna to uh, objects like probes, deep space probes, but unfortunately, I could not get any signal. So, and I didn't know why. Could have been wrong. The azimuth and elevation data, or something else. So it was too many uncertainties, because at the first place, I don't have any reliable source that like a beacon, so I can point antenna at the beacon and try to adjust back and forth the feed, identify the problem. Do I receiving or something? The signal generator certainly worked, but the overall system as designed didn't show the sign of the expected performance. So therefore, I decided to remove the system to save it time and try to identify what's going on and run the bench test. The bench test turned out successful, and I was able to adopt more SDR receivers than initially planned, and find out that there are possibility that the filter itself that mounted in our F assembly, due to mechanical forces that we were applying, probably was off the band. So when I removed the filter, the reception was a lot stronger. So there were some challenges. So I didn't have to be honest, any valuable results that I can share right now. So we're good. We detected something and we're moving forward. But there was kind of learning curve. We identified things we need to do from a mechanical perspective, that Roger going to work on his end, as well as on my side, from the software and the hardware perspective. Everything is laying down on here, on my bench, ongoing testing, trying to adopt a new SDR receiver that been gifted to a DSES. It's equivalent of B210. It's about $5,000 receiver that used to cost. Right now it's about goes $1,500 on the market. So it's a very professional, which I'd like to use it for DSN system, and as well for upcoming EVE projects and other projects we're going to be involved with the weak signals. I don't have anything to update regarding the DSN, so my next trouble is going to be on January 12th. January 16th to 18th, and I will bring the system that already new upgrade, that has the new upgrades and the new software, fully utilize the new module that I designed, as well. I'm going to bring the beacon. So Rick also going to come. Rick Hembley gonna be there, and we both gonna be testing the beacon system on 8.4 gigahertz, about 2 or 3 miles away from the dish. So that also give us a good reference point from the pointing perspective of the antenna, because apparently there is a sweet spot due to west from the site that's actually 270 degrees exactly. So which is perfect placement for the beacon, so we know the pointing antenna with the narrow beam width will know that we're pointing there. Because Roger had another identify another issue that well, it's not an issue, kind of observation. I don't want to say issue. It's observation that the actual actually I'll let Roger to talk about this. It's kind of affecting the DSM itself. Roger, do you want to add something about that? What we observed?
I don't know why I'm getting such an echo. Can everyone mute? If you could mute Alex.
The echo is coming off of Alex's feed.
It's coming off of what? There we go.
There you go. It's
How's
off
that?
Alex's feed. Yeah.
Okay. Alex, are you talking about the horizon elevation 0?
Correct.
Okay. So let me see if I can share. I'm actually, for some reason, my mouse is hanging up here, and see if I can actually share. Okay, I can't share. I'll work at this as I'm talking. So, we put laser level, actually, construction both vertical and horizontal level on the hub, and we found out that that our zero elevation is actually a little bit less than the zero elevation that currently reads out from the software. So, which then got Alex thinking about the fact we don't know if this telescope is zeroed all the way around. It could be after 60 years it has some list to it. So that's an interesting experiment to look into. And so Alex was talking about something with a inclinometer or a gyroscope to just check our level, our zero elevation all the way around. Okay, I think maybe I can start getting to sharing here.
Yeah, and while you're doing this, I want to clarify about the gyro. So nowadays we have technologies that allow us to do kind of complicated things in a very simple way. So an idea is to have 3x gyro, which is tiny board with a sensor. It's a little bit more sophisticated a gyro than you have in your phone, right? When you move your phone up and down, left and right, actually inside the gyro tells what to do for the screen and all that. So basically the same idea, which is going to be connected to a sort of device that's going to stream real-time data. So, and we can mount this on any axis on the dish, and we can just rotate the dish and see the readings from that gyro. And gyro are precise because it reaches the magnetic earth as well as the internal sensor. And I've used this professionally at work on numerous projects. And we can use that as the indicator, additional indicator, to see if we really still horizontal plane when we do 360 degrees rotation, as well as the elevation from 0 to 90 degrees. So it's additional to what we have for verification purposes to see we're still what we're supposed to be.
Alex, how about the drift of gyros? The magnetic gyros, they drifted. So if you use laser gyros, they're more stable, but magnetic, they drifted.
Yes, and you know precisely what drift is, you can compensate that. So you have to calibrate first before you run the test. So.
Okay.
And a laser is way better than a laser gyroscope used on the airplane, Boeing 737 and any other for the navigation purposes, but extremely expensive.
Okay, so this is so we took this laser level up there and found the basically marked the hub for vertical and horizontal center, and then that allowed us to look at least for the elevation. We tweaked the dish until our horizontal line was through the center of the dish. And then when we put the feed in here, you can see there's a little cross on the feed there, up and to the right of where the actual lasers cross. So I have to tweak the mount a little bit because I can't go any more left and I can't go any more down. And so I've got to fix that. And I'll just kind of flip through these pictures fairly quickly here. So this is actually, Alex, you might want to talk about this a little bit. Go ahead.
Okay. So basically, this is what the entire DSN system is, and that's kind of like not. I mean, I don't like the way it's all laying down, but that was the temporary one just to verify the system health. The system is still functional. It is still functional, and couple key points here. Everything that you see, it's only uses two cables. The one cable is a fiber optic, which is we remote using just remote desktop from our PC computer on the control room to the internal Raspberry Pi. So we basically remoting from the Windows environment into the Linux environment, and it works amazingly great. And then everything that inside this box is all our scripts and control systems and everything. And when we're talking about this box, it's literally about 7-inch by about 1-inch height, and the thickness about 1 inch, and about 7 by 5 box, aluminum box. Everything is in there, and the other one is just a power supply that I had temporarily put in there to feed it, which is 12 volts, which runs out of 110. So we need just 110 volt connection to run the power supply and fiber optic. That's it. This entire system. The new system, it has a slightly bigger box. It has a more powerful computer and more infrastructure inside, as well as the additional computers. There's a two in one. And there's a white cable is the control cable that drives the steppers that allow the entire assembly slide forward or back, and also controlled remotely. So by indication, what is indication? How we know what's our basically reference, right? The idea of reference is that we have the constant signal, and the idea was to point antenna to any constellation, any stellar objects in our galaxy that generate the noise on 8.4, but unfortunately we could not find any reliable sources. And also the fact that the Earth is rotating itself, it makes things complicated. So we need to have a reference on the Earth. So, and that would be the desired way. And that's what we, after a conversation with Rick, we decided to have a ground-based beacon, low power preferably, and using as a reference miles away from the dish, and by adjusting the feed back and forth, we can actually find the sweet spot where the focal point is. And that's going to be very good information, because I don't know until now if we don't know what the focal point is. We assume that that's 2 feet from the edge of the flange towards the dish. It's the feed point, basic calculation. But there's a lot of factors applied to that. If you're out of the focus, you're still going to receive. It's going to affect your gain, and we never verified the full gain. So anyway, scientifically we never proved, but that's the point, is the actual focal point. So we're trying to verify that, and we have a certain way to do that. So this system not only will help us to detect deep space network probes, but also allow to calibrate dish in a way and form, shape we need it to possibly improve the performance, especially helpful for EVE project, to know that we're missing something or needs to be done, those kind of things. So anyways, that's what approach we have.
If everyone turns up their volume, this supposedly, if you look very carefully, you can see the feed moving forward here.
Yeah, you can actually see it, not only hear it. And this is applicable for any feeds. So it's not just as tied to DSA. So tomorrow we want to do something on different frequencies, perhaps going higher frequency or lower. Even science feed on a hydrogen line, 1420 and 1690, on anything we use, can be also done there. But how often you need to slide antenna back and forth? Not really. As long as you know what the focal point is, regardless of the wavelength, regardless of the type of a feed, you're still going to be at that point. So that means you don't really need to have ability to adjust the focal, move the feed back and forth. It's only for the identifying the initial focal point, because I don't think we ever run at 8.4 gigahertz on this dish. In fact, this dish was designed to operate in those frequencies, an X band. So it's for us, it's kind of a study to understand where the best spot for that, which can be also used for all other feeds we have. The 1420 for hydrogen, for pulsars, for masers, and as well for EME.
And that's all my pictures.
And I heard that Paul said that the video, he already ran the video, right? Where we were testing the feed.
Yeah, I think there's a link for it on the web page as well. So if anybody wants to see the action inside the control room.
Okay, and the last thing I wanna just to show the software to operate in real time. Shouldn't be more than 3 minutes to run that. Kind of close the subject about DSN. So it's basically the last. It's not only hardware side, it's also the software side that will allow us to detect what we need to detect. Majority of the deep space, what is a deep space called? Everything that exceeds the orbit of the Earth, considered deep space. Simple as that. So if something orbiting around Mars or Venus or Sun, it's considered deep space. And as we know, the solar system by itself, it's big. So something orbiting Mars, orbiting the Pluto, would be considered still deep space, but the distances would be completely different. So, and we have now probes all over the solar system, starting from the Sun itself, which is closest to the center of our solar system, as well as the I'm not talking about the Voyager because it's beyond the solar system. I'm talking about the Lucy and New Horizon that orbiting towards the end of the solar system. So we have a lot of reference points for us to do it. It's going to be very cool, not only just detecting it, but it's also verifying things like velocity. So if you can track the Doppler of the object that you're receiving, because you'll see the Doppler shift. By the shift of that Doppler over time, you can calculate what the velocity is. And also you can calculate is its object moving away from Earth or towards the Earth. Because some deep space is orbiting something, like a Mars reconnaissance orbiter, or lunar reconnaissance orbiter, or Stereo A, which is orbiting the Sun. So they are moving. So they are at some point they're flying away from us or flying towards us. So not only just detecting, but also verifying the velocity and comparing what actually a velocity posted. So it's kind of cool experiments. I think that also students going to be very excited to copy signal from Voyager or New Horizons or Lucy. Those are three probes that flying currently over 600 million kilometers away from the planet Earth. So I just want to run the software that allow us to do that. And if anyone has questions, please let me know.
You don't forget to mention the Artemis stuff. That's applicable to them as well.
I'm sorry, what was that, Paul?
The Artemis work. This will apply. It will apply to that as well.
Yeah, I can combine both because it's actually on the same computer. So what I'm going to do is I'm going to actually share. Where's the share button? All right. I'm going to share my Linux computer, and please let me know if you guys see Linux.
Yep.
Okay, so I'm remoting right now from my Windows to my Linux, where I'm running my software. So this is the DSNSDR script. This is all Python script right here. I've been working, and a big chunk of that rework actually done at Haswell. It's great environment for me. It's nobody bugging me, and that was kind of a more efficient time. So this is kind of main window. It's not organized, doesn't look professionally. Honestly, I don't care. That was the intention to have nice black window and all of that. It's all about the performance. So we have a tab of the SDR. We can choose the SDR. In my case, it's going to be Pluto, but you can choose AirSpy. Actually, I was able to integrate the B210 as well when I was there, so it's actually fully functional as well. You can use RTL SDR. By the way, this software going to be posted on our groups.io. It's open source. Anyone can take it. They can use it. They can run it. They can modify whatever you want it. It's fully functional. And then you choose your target. Let's say Voyager 1. In this case, it grabs the data from the NASA file that built in and calculates what's the frequency. It was actually picks the data from there and knows what relative velocity is. What would be Doppler shift based on our location and current time. And then the middle part is the signal processing. It's what we want to plot, how we're going to plot, what kind of calculations we were going to add to it, and etc. Then I added some GPS location. It actually gives our precise location of our antenna. So if I place this module, the GPS, on the feed, it will calculate exactly height, the altitude, as well as the coordinates based on that location, with the accuracy what the GPS has. So it's good to have, other than just using just numbers from Google Maps or something, but not necessarily are correct. This gives us a precise. So I'm not running GPS right now, but if actually I am running. Cool. So if I start GPS, I'm streaming data from USB port, and it gives me my location right now. Well, I'm not in Haswell, I'm in Chandler, Arizona. So I reached 384 meters, and our current coordinates, as well as being locked on 7 satellites. You should know by now that only to lock the location you need only 4 satellites, 3 for position, 1 for time. So we have 7 satellites. That means we're 100% locked on the position. And on the observatory we choose K0PRT. It's already preset. Or you just copy from GPS. So click copy the GPS. It copies exactly what has been GPS was reading. But well, this is not K0PRT. Unfortunately, it's K6VHF. So I'm going to use the K0PRT, just a preset. And then when you're ready to do that, you just start the spectrum, and it will start the. There we go. And it starts the main window where I call this detection. So we're off actual real time. We can see the signal. So just ignore this in the middle. It's the typical SDR DC issue at the 0 of the filter. So it's not actual signal. But if you would have a signal here, I don't know if I can generate right now. It's probably I can, using this small generator. But if you're going to have a signal here, the algorithm is very simple. Detect the signal and start integrating. So it's called program system integration. So it adds, every time it captures the signal, detects the signal, it adds to it. It's integrating. So if you have a very weak signal, you're not going to be able to see it in real time. You need a certain time to integrate. So it's like right here, you put, let's say, 300 milliseconds, and that will get you better integration time. I'm starting the game. There we go. So now the system is ready to detect the signals are going to be within 300 milliseconds of integration time. And so why is it important? It's important when the signals are having very small signals noise ratio, basically below the noise floor. So we do expect the Voyager not going to be easy target for us. So the integration time is very important. It's extremely important for projects like Venus, bonds like Apophis, and other experiments we have. So it's important to deal with these small signals. So anyway, and they have multiple charts here. The first is a spectrum. I have a max hold, so if the signal appears and disappears, let's say some deep space probes are modulating, turning on and off signal, they're not constantly transmitting. So if you have transmitted something and turns off, this signal remains to be visible on the graph. So that's why it's already integrated in the software. And also we can see what the type of modulation is. Majority of the downlinks are using QPSK modulation, so it's everything that phase shifting keying. So we can able to see that modulation, and I've been asked if we can modulate, decode the signal. Yes, it is possible. So the decoding algorithm is posted on NASA website for each satellite, so I can simply integrate those algorithms, and we can actually decode telemetry. I think Roger, you asked. I remember you asked me that question. So and we can actually decode telemetry, and that could be the temperature, it could be speed, whatever the satellite sending data to ground. So we can actually decode. Kind of going to be cool too. And then we have a waterfall where we actually visually identify the signal, also the Doppler drift. But in this particular case, I'm actually locked to Doppler. What that's supposed to mean? That means I'm tracking Doppler. So I want to see the signal always in the middle. I don't want to see the signal going to be somewhere off and going to be drifting. That happens when you don't have any corrections. Like if you open any SDR software or anything you have and then connect your SDR receiver and you detect the signal, all you're going to see the slanted line over there. So what that means it's flying, you have a Doppler shift, and that tells you that this is something is flying from in space at a high speed. And here you're not going to see, flat lines, vertical line, because the software corrects the Doppler. I can uncheck that, and it's going to be in a way how it is. And then narrow band spectrum basically takes a middle chunk and about plus minus 25 kilohertz, and you can see in there. So basically, this is the detection software. Very simple, nothing complicated. You can real time, but you can also use for anything you want. This is the spectrum analyzer, the spectrographer, so-called, and you can add any targets, any frequencies, anything you want. In our case, it's 8.4 gigahertz. That's IF now to 400 megahertz, 432 to 450. And what we're working here is working in IF. You see it in the middle, say IF. So it takes the 8.4 gigahertz from down converter with built-in LO 7.9 and down converts to 452, which you have a small SDR receiver connected to that output, and we can only receive on SDR the IF band, which is 452, and it's interpolates to 8.4 with the Doppler. So anyway, it's those things that you need to be sure you're doing it correctly. All right, anyone has a question about this particular software for DSN? All right. Now we're going to move to Artemis. So that's the Artemis GUI, the Python code. Gonna start it. Okay. So that's Artemis 2 Doppler logger. It's been created for Artemis project that we might be participating. If someone doesn't know what Artemis 2 is, it's the NASA mission to Moon. Take the astronauts to the Moon. So eventually orbiting Moon like we have ISS. So it's a significant milestone for NASA. So hopefully it'll be successful. They already had some previous launches for the rocket called Orion itself, and Artemis 2 is a mission. So I posted this all details on the groups.io and under Artemis 2. Take your time and look up. There's all information with the links. This is the latest software we have. Current revision is the 1.2. I updated at 11 during the Thanksgiving. So the software has all the revision listed here. So what changes were, as well as a manual. So anyone want to run it? So there was a manual how to run it. So if basically what we need this for, and what is the Artemis 2 Doppler tracking, why we need that. So NASA wants to precisely calculate the speed from multiple points on Earth, the speed of the rocket, flying away from Earth towards the Moon, and when it comes back to the Earth. So it's very helpful information because there's a lot of things could happen, and there is no such easy way of measuring. So that's why if you have a multiple stations that receiving signal from the same source, which is the rocket, they can each station can precisely calculate the Doppler using the precise GPS synced time and the receiver, right? By knowing precisely this stem time period, this point of a time, the Doppler shift was this. you can easily calculate what would be the relative to Earth speed. So, and that's what the NASA wants, and we've been asked if we can support that. So we sent our proposal and waiting on the response from NASA. But meantime, I decided to create the software and design the hardware to be ready in case if we need it. However, this software is not just for Artemis. It's even called Artemis 2, but that doesn't mean nothing. It's basically universal software that DSES can use as the Doppler tracking software for any object. Anything that transmits down something, let's say, any rockets, any spacecrafts, anything, as long as we copy the signal, we can actually precisely calculate the speed of that vehicle. So it's potentially useful for any other missions, or perhaps that Blue Origin working on their lunar system. So it potentially will benefit DSES in the long run to use it. So there are a few features in there. We can use a simulator, which is going to simulate the signal. Straightforward. I don't have any hardware connected to me. I want to simulate what's going to happen, so I go to Simulator tab. I want to do like a stereo. It's the solar orbiter that takes all these precise, beautiful pictures of the sun, and we're going to do a mission. So basically, I simulate the stereo mission in this case, and all I need to do is just start logging. So, and it represents the signal being transmitted from stereo down to Earth, and it's changing the amplitude because it's modulated signal. And what we're doing, we're just tracking the Doppler of it. So the software has this module inside that's simulating the actual satellite, that what emission does. It turns off and on and off sometimes. Switches from high power to low power. Right now is a high power mode, and then low power mode. So anyway, I took the algorithm from NASA that uses the same algorithm for actual mission to test the software. So as you can see now, it started moving. So before that, your Doppler was kind of straight, and then all of a sudden the Doppler stopped shifting. It tells you the satellite moving now, and based on the range rate right here on top of the screen, it tells me that the satellite now moving 760 meters per second away from Earth, and signal is super strong. It's 88 dB signal noise ratio. So it tells the story what's happening. It's kind of hard if you don't understand what you're looking at, but I opened a little bit bigger one. So here you see that the Doppler trending up. Basically, this vertical line is a trend line, but it also tells you in which direction it's moving, and moving away from Earth at a speed of 800. So anyway, that's a simulator. I can pick a lunar orbiter as a reference, but it doesn't matter. It won't make any other differences. Stop.
Alex?
Yes.
Wait, you mute for a moment.
Oh yeah. Sorry. Where's the mute?
When you say away from Earth, I just want some specific here. Are you taking out our velocity from of our sight as the Earth turns? So it's basically the velocity away from the center of the Earth, or is it the velocity away from our sight?
Well, our sight it's on the Earth, right? We're moving with the Earth, so they should be no two reference points here, right? There was only one reference point. Our antenna or Earth, it doesn't matter. It's the same position, right?
Well, it does matter because a different location would measure a different velocity.
Well, exactly. That's why you have a station, right? Coordinates. So of course, if you change the coordinates, everything going to be changed, right?
Okay, that's what I was asking. Whether it's factored out our velocity or left it in. Okay.
Yeah, it's a legit question. So Roger,
Alex?
Yes.
Alex,
Yeah.
the Earth is rotating. We're on the Earth, depending on whether we're approaching or going away from the satellite ourselves. That's going to be an additional change.
Yes, that's true too. That's very actually good question. Yes, it's already compensated there as well, because Earth rotation is a constant, right? It's not moving over time, right? It's a constant. We know, like position for the moon, right? It's a constant. What is as well as a satellite, because satellites follow. I'm using the Empress from the satellites, and well, Kepler elements or whatever it is, or spice components, and there's so many names for that. It's already predicted. So because I don't get an assumption I am calculating here everything. No. I'm using the file from database from NASA that has everything there based on Earth rotation, which compensated. All you need to do put your coordinates to compensate that. So basically, you're gonna have, if you're looking for accuracy, what is important for accuracy is that your precise location where you're at and the time. That's it. That's only two variables, two important variables that will affect the Doppler, right? Everything else is the module. It's already predicted. So when NASA creates a database, it has three different modules for the same object. One is the previous, current, and predicted. So predicted means for next 2 years ahead. It's a computerized modeled prediction. So I'm using this modules, and where is that? It's like this. It's a BSP files. So anyone can go on the NASA GPL website in file directory, and if you have an account with NASA, you can actually go to FTP server and get those. So this particular script, it grabs the data, or it's actually asking, do I have a local data? If it's not, it's actually downloads from NASA website, and this is how it uses. Any other questions about Doppler tracking, positioning?
If this was trying to track an object that we did not know what the original frequency being transmitted was, how would we determine that?
So if you don't have the file that or like common database, one of them is like a D421. D421 is the file that has all stellar and solar objects in there. So NASA grabbed everything that we have in solar system currently and dumped in one file. So like when you track moon, or writing any codes for Venus or Pluto or anything that flies, like DSN probes, that particular file already has it. So if you don't have anything and your file can't recall that information, you're just tracking, right? You just pick up some signal and you're tracking. All you can do is just to see the Doppler changing positively or negatively, right? Goes in minus or goes plus. That's all you can do. And based on that, Doppler, basically see on the slope right here, is actually calculates all this slope. It's a hertz per second change, and what is important, second, because you have to be precise on that second, which is the rubidium or any other discipline GPO should lock to it. So it's your seconds are off, or your time is off, all calculations wrong, and as well as your Doppler shift wrong, velocity calculator wrong, everything wrong. Is all based on timing. So yeah, I mean, you can't tell what the object is, but you kind of can tell which way it's moving, away or towards, as long as you know the rotation of Earth. Earth is rotating only one way, right? It doesn't rotate back and forth. So it's also easy to calculate.
I'm thinking like an object like 3I Atlas. If that comes into the solar system and it starts transmitting, how do we know what frequency it's transmitting on?
Well, I would approach this way. So if it starts transmitting, so you know what the position is, right? I believe we can point antenna towards that area of a sky where the object currently is, right? Then you look in the spectrum of your receiver, right? So, I mean, obviously we can't cover all frequency ranges, right? If it's man-made device or it's, I don't know, extraterrestrial made, device that it could emit in any frequencies. So, we cannot cover, but if we capture the spectrum coming out of that, right, then we can use that particular frequency spectrum to decode. But this particular, so Artemis, it's only tailored to S-band, which is 2 to 4 gigahertz, right? Because that's what they asked us. But if tomorrow we want to have capability to go from 1 gigahertz to 10 gigahertz, I can simply add that simple command to the SDR receiver to which frequency you should tune. Now the Doppler are going to be different because it's different frequencies, so obviously it's all going to be calculated now. But yeah, I mean, it's a good question, but I don't know if it's there a real correct answer. As long as you transmit within S-band, yes, you can detect it here. But if it's outside of the S-band, right now, we don't have that.
Okay. Thank you. I just wanted to know, I wanted to be ready for 4i.
Yeah, we certainly can get ready because, it's funny you mentioned 3 Atlas because there's a lot of conspiracy theories going on around that object. And, as being part of this society, it's kind of also like, WTH is this, right? So anyway, I like this question, Floyd, because, things like that, we can always add to the software, right? Because my mind was strictly at what NASA wants, what we can deliver, plus additional flexibility. And let's talk about flexibility at this point. So we have a clock reference indicator that grabs the data from the SDR and tells me that, hey, I'm getting clock frequency, so I'm locked. Actually, to check that, if we connect to SDR, there we go. So we're connected to SDR, and as you can see right on the bottom, where under the start login, you see say connected to Pluto SDR. As well in the middle, I added the status command. You see this connected to Pluto SDR, and as driver reported that I'm a 10 megahertz reference lock. So it tells me, what, the system is healthy. I'm connected to SDR, and I'm actually ready to, receive. So, but you got to move through all these tabs and see, okay, if I want to do Artemis 2, yes, the actual transmit frequency is 2216.5, which is the frequency I found online, and that's what they provided that this possibly frequency going to be. But if frequency is different, as a matter of me going to the code and tweak it, because I don't have that. No, I do have it. Yeah, I have that variable right here, so I can overwrite this. I have a default number, but I can overwrite from here what the other frequency is going to be. And by the way, that also answers your question. If we want to go to different frequency, we can type that frequency there as long as your SDR receiver covers that. Sample rate, well, it's the standard sample rate, 2.5. I use this for both for AirSpy and Pluto. But if you do like a B210 something, you actually can go 5 and 10 megabit megasamples per second. So it's kind of neat. The gain, it's 10. You can add gain whatever you want. It can go 50, 60, but it's going to be too noisy and not needed. With our big dish antenna with such a big gain, we don't really need to increase the gain of the SDR. I would even keep it 0 to be as low as possible. It's all defaulted here, our antenna. So we have 18.2 and 0.55. It's kind of conservative number. I mean, we don't know what realistically we have. I mean, unless if I can ask people that know what our efficiency of our dish from 0 to 1. 1 is the ideal, which is that is exist. So, I mean, if I'm going to ask someone, we're going to be probably around 0.6, and that's the real. 0.55, it's going to default. I'm not great, I'm not too bad, but I'm kind of like in the middle. So 55 is kind of in the middle, conservative, but we might be efficient more than that, which is improves a little bit the gain of a dish. But I didn't want it's not important for Artemis because Artemis signal is going to be pretty strong with our antenna gain, so we don't really care are we slightly off or not. but I do have capability to option if we know for sure what the efficiency is going to be. Station, again, same thing. We need to know what our station is, and I have a preset for Haswell. But once again, added my GPS tab. It's right on the top on the right side, so I can stream data from GPS. It's real-time data, and I can copy that data into this. So software will calculate based on that. But once again, I'm not in a Haswell, so it's inaccurate. So we'll go back to the preset. So anyway, processing logging as FTT size is basically the spectrum size. It's nothing. I think everyone that will use SDR or any SDR software very familiar with that. Except integration time, I can add more integration time, but it's also for this particular Artemis is not important. If we're going to deal with the very weak signals, we can actually improve this integration time to put 30 seconds in that already capable to copy signal from Venus, or 300 seconds to copy signal from even further. So anyway, that's that. We have that as well as the those are default. Doppler analysis added some residuals for the slope itself for the Doppler. It's kind of additional data which you have, but it won't hurt. It was easy to add it. Is it helpful? I don't know, but it'll get you a lot more numbers. If someone asks, we have that. And it saves in two formats. Saves in a CSV file, tabular data, comma separated, as well as the NASA TDM file, which NASA asked to have that. Lockheed guys asked us to have that format, so it's there. Everything that you can name the file you want it, and this is the folder where all these files are. So I've been running tests. Obviously, we have all these files already. Oops. Okay. And then you can export the report after completion. You can export all this numerical data and the plots in the format of PDF. The real-time plots, it's what you want to see. If you want to see just a Doppler versus time or spectrum, that's two plots are default. If you want to add a waterfall or IQ constellation, I've been asked what's the IQ constellation, so it's basically the modulation, what kind of modulation is, but they really need it, we don't care. There's got to be some type of modulation coming from Artemis, but that's again, it's not our priority. The signal going to be slightly going up and down on the amplitude because of a modulation loss. We don't care again. Waterfall, just a visual. Waterfall settings, you can set whatever you want it. Don't care, or all default right now, and called auto scale. Anyway, so and this is logging system here. So if you go to actual right now, the actual, and we ready that we detect a signal from Artemis. So all you're going to do, connect to SDR and click start logging. So in this case, you just connect it to our SDR, and as you can see, you're just reading noise. There's no signal. Something in the middle between, once again, ignore is a DC. It's the issue of every single SDR. It's when you center to the filter of center of the filter. So it easily can be nudged out if you need it. I say I didn't care. But as you can see, the scale here, it's just a few dBs above the noise, so really, really tiny. So I'm going to simulate now the Artemis. So this is the Artemis Orion rocket. So I'm going to transmit on 2.2 gigahertz, 2216.5. I don't want to do 115. Okay, hold on a second, please. I'm gonna change the frequency. Oops. I think it's got low battery. All right, so I'm transmitting signal on supposedly exact frequency, and as you can see, you've got a signal right there, right in the middle, which represent the downlink signal from the Artemis towards the Earth, and we're receiving it. And if I open bigger, so this was just a noise going up and down, and the software recognized that DC it's kind of signal, that's why I had that. But this is how the Doppler should look like. So if you run this over a period of hours, because of drift of the generator, because of drift of the LO, you'll see the lines going to be going either down or going up. I ran it for 2 straight days, and I saw the drift of my GPS discipline. It was within a few hertz, so it was kind of pretty neat to see within a few hertz. But in this particular case, because I'm transmitting constantly, it collects all this data and identifies that with this signal, the speed of a rocket is 1392 meters per second, based on the current Doppler, which is kind of above the frequency. So that means it's flying at a minus, away from the Earth. So in here, it takes 1 second and breaks into milliseconds, and collects data every, I believe, 100. No, it's going to be 250 milliseconds, something like that, and captures the frequency, captures the Doppler shift, calculates the range rate meters per second, and as well as the signal noise ratio. Because signal going to be fluctuating, but distance between Earth and Moon, there is not much free space loss going to be for this signal. There's probably going to be a few dB difference, so its numbers not going to be changing too much, and we expect to get a very hot signal because of our gain on 2 gigahertz. So we might need to even reduce the gain of our SDR to prevent oversaturating. I'm not sure exactly what the output power and antenna type on the downlink has been on the space rocket, but you know, when we get that data, we can actually precisely calculate. So, and when everything plotting is automatically, there's no participation involved. We can keep this. I kept this for days, for 3 days, and make sure everything is running. There's no bugs or something like that, and it was running very good. So basically, this would be your Artemis if we're gonna be participating. And if I'm gonna change the frequency now, let's say I'm gonna shift the frequency a little bit different way. So instead of 5, I'm gonna do 6, or actually gonna go other way around to 4, and activate again. So I'm transmitting slightly off from center. So now, as you can see, it's right off the center, and you see your range velocity is positive now. So it's rocket flying back towards the Earth. So, and here, as you can see also. So this is kind of valuable information. Down there, it's basically Excel function. If you ever use the Excel plots or something and trying to analyze the data, and you use the same equations for the trend lines and the slopes and everything. So it's no different here, except we're just using the Doppler data, like hertz per second. So what's our change within 1 minute to 60 seconds? As -1 hertz per 100, or it's actually 1,000 hertz per second. Because it takes the entire data off this plot. So we were flying away, and all of a sudden we're flying back. So because I changed the frequency. Anyway, that's how it works. This is everything you need is just on this plot right here. You can size the way you want it. You can save it, and you can keep it over time. If you know any other objects you want to track the Doppler, you can use the script. You can modify, you can add modules, you can add calculations, so whatever you want to do, it's fully flexible to do that. And then at the end of the day, when everything is completed, you just open the folder with the file you want it to be. I don't know which was that file, probably, probably this one. Yeah, and the final data, it looks like that. This is the file that I wanted. Things gonna be renamed a little bit differently, whatever they want it. We don't have Rubidium GPS. We will eventually when Rick brings that. And basically that's all numerical data. Besides what you saw there is actually all plots and collects all this detailed data down the file. And there is numerous of those files exist, and it generates continuously. The internal memory of the module that I built is 1 terabyte. There is no way you can ever fill it up, that memory, with all those files that we created. Anyway, I'm done. Any questions? Cool. No questions. I did a good job. All right.
That's
I
amazing.
have comment.
Go ahead.
For all rocket launches, there is a possibility to get telemetry from the rocket, because for any rocket launch, it is an open section of telemetry, so you can basically decode it, and it will provide direction, speed of the rocket. So that and it's standard protocol, so we can actually get telemetry from the rocket.
And you know, good point of that, Vlad, is that with this system, you can run multiply scripts and have multiply SDR receivers tuned on multiply frequencies, so you can simultaneously receive signal from the we call this launch vehicle, right, and as
Yes.
well as a payload. So it's, you know, I anticipated questions like that are gonna be, right. That's where we're flexible, and that's why I pushed to move to DCPM module. Recently, I designed and described on the group's IO. That is capable to track simultaneously over, I don't know, maybe 20. I mean, I'm using 8 USB 3 8 port hub on one computer. You can put another computer same. You can have 16 port, doesn't matter. So you can use multiple SDR receivers as long as within the passband of the feed. And yes, you know, if rocket transmits on 22.25 and the other transmit on 22.16, certainly we can copy both of them. So the software has capability, do that. The hardware has capability. The question is the purpose. Do we need to, right? If we can, we can.
And one more thing, this is polarization, antenna polarization for the space probes. So that 10 gigahertz feed, is it linear polarized or is it circular?
No, you never use linear polarization for any space objects that are moving. So obviously everything that NASA launched, it has two polarization. Every single probe that currently exists in their life has right hand and a left hand circle polarized. So that means you on the Earth can just use either one. You can use, normally people use right hand circle polarized, but in our case we have both right and the left hand circle polarization. We're using septum feed. It's been donated by W1 gigahertz. Thank Paul for that. So we can switch. So if we see signal fading out, or they switch from right hand to left hand. Like for example, Voyager, he had both polarization and had both TWTs, so have both amplifiers, and had another set of amplifiers. I had 4 amplifiers, 2 amplifiers per each polarization. 3 of them died, and a circle polarization switch died. So they only had chance to route one remaining TWT, which is travel wave tube amplifier, into whatever left over the switch stuck in the position, and I believe that was left-hand circle polarization. So on the Earth, you need to have right-hand circle polarization in order to copy. So anyway, regardless of that, we have capability to receive both of them.
Okay.
Thanks for questions.
Alex, I have a question for you. If there's a modulation like QPSK or something else, does the frequency modulation put noise on the Doppler? Is the Doppler looks like it's got a frequency variation that's due to the modulation of the carrier?
That's a good question. Well, all what I had, I did not see or any suggestions or recommendation. I do have the module that applies the module called modulation loss to the signal, But I never heard about that the modulation itself might affect the Doppler. So because I can actually verify that by using any object, space object, that transmitting in the QPSK or any other phase shift modulation, and verify that. And the other way to verify that is actually Beacon, that gives you CW and QPSK modulation, and then switches to CW and then QPSK modulation. That also will tell you if I'm tracking Doppler on CW and then QPSK turns on and I have and the software confusing what the Doppler is, then definitely it's going to be guess. But as far as I read it, Don, I did not see a suggestion that's mandatory to implement, but it's worth to verify it one more time.
It might, like for QPSK, it might actually integrate out.
Yeah. Yeah, I'm gonna read this tomorrow because I'm kind of curious. Is it worth to implement, and what kind of implementation gonna be? I mean, is it QPSK as a phase? So amplitude. What I know for a fact, when you doing CW, you have a certain level, let's say 20 dB, and then when you start modulating, you lose about 3 dB off that. What comes to digital modulation, so your signal reduces down. And why for me was important when I was doing simulation, it was kind of important to understand I'm simulating. I'm actually adding 3 extra dB for no reason because I'm not accounting for the modulation loss. So, and that's why I implemented this modulation loss. And different space probes have a different type of modulation, so the numbers were slightly different. And actually, NASA file that has it that. I didn't utilize it. I just directed the variable into the NASA file. Hey, grab the modulation and apply it, and so I did, and it works no problem. Great question. I love it. Yeah, that's something that directly might affect the signal, and Doppler, which is the prime function of the software. Any other questions before I stop sharing? If anyone wants to run something. No? Okay.
I have a quick question. This is in regards to use of the beacon at the 8.4 gigahertz for alignment of the dish. And as far as I'm aware, there's not really any amateur ham bands in the 8.4 gigahertz range. So I'm just curious in terms of legality and possible FCC implications, utilizing a beacon at 8.4 gigahertz at some distance in order to align the dish, if that would entail some kind of infraction of FCC regulations.
Well, the beacons is below 1 milliwatt. Actually, FCC regulation 10 milliwatts. So everything is above 10 milliwatts needs to be regulated, but everything is below 10 milliwatts. I absolutely don't need to inform FCC or do anything. So that's easy. But beacon, we don't really need to have a high power. That's the whole point. We need to have a low power as possible. And I have all hardware, and I'll just need to put together to make it happen. So, like a simple example, this is the generator, which is everyone can buy off Amazon. I don't know, like $20, something like that. And it goes from 25 megahertz to 6 gigahertz. So I wish it's gonna go higher than that, but that's what the ADC, or it's not ADC, the hardware is maxed out with 6 gig. So what I'm gonna do, I'm gonna use the additional LO, and I'm gonna use this as the IF, and I'm gonna put this all in the mixer. I'm gonna put the filter on 8.4 DSN system, so I'm gonna extract the actual 8.4 signal. But I also want to add capability so I can actually enter and change the frequency if I want it. So like perhaps small Python code or something else, so I can control my generator, the signal generator, to change the frequency if I need it. Why is it important? Because I want to add modulation. So since Don mentioned right now, not only CW, I want to add, let's say, built-in QPSK modulation sending K0 PRT, like a beaconing, right? Doesn't matter. Or maybe Q65, easy. Something like that implement, as well as the implement other features so I can, replicate something like what we need for the future, what projects we're working on. So that's going to be done, by the way, before January 16th. So if anyone want to come and witness all of that, that would be good because we're planning to use that. And the signal, 1 milliwatt going to be plenty for the beacon to us detect from a couple miles away.
Couldn't you just use that signal generator and run its output through a frequency doubler, little nonlinear frequency doubler, and get that output?
Yeah, it is possible, but it limits me to features. So I have like modulation, I don't have ability, but Doppler it will give you like perhaps harmonic something, and I do have a Doppler, by the way. I can multiply by 2, but I want to have more like a more universal approach. Let's say it's not like I have hardware. I just need to put it all together. But yeah, I mean, you can certainly do that. That's the easiest way. I have a Doppler. Right? I have a passive Doppler and have active Doppler. So passive Doppler, kind of you're gonna lose about 8 dB or something in there. But I can go with this about plus 20. That's dBm. If I'm gonna put small horn antenna or something, that's gonna get you a lot more ERP. But yeah, I think it's an easy way to do that. In fact, since it's been mentioned, I can actually try that too. Any other questions, suggestions?
Why we just don't use some of the GeoBird as a source of signal? Because telemetry, most of them is S-band, and they have beacons.
Well, I'm not. Yeah, I don't. Not everyone has beacon there, but once again, that's involved the dish rotation. So, and you have to, you have to point there, and we can use one as an option too. But the beacon is we want to do is just not only for testing the system itself, but also aligning the system, and as well knowing the you kind of mitigate these propagation issues, losses, and everything.
Yes.
And that's kind of important. Like if I said 2 miles, there would be, even though it's 8 gigahertz, still the concern going to be if I point antenna down, and I'm going to read the noise, thermal noise from the surface. So during the daytime, when we have a sun that warms up the Earth surface, it actually changes the noise characteristics on 8 gigahertz. So you might read this noise, but it's insignificant to what we were going to do. But when we get to a point that we adjusted feed, we're getting certain reception. Because it's easy for me, if I know where they have a 1 milliwatt power measured into dipole, which is, there's no gain, right? We're not talking, 2.15 depth. We're talking about 0. So we have no gain. So I know what's the gain of my system on 8.4 gigahertz, based with the size of a dish, right? And I know the distance between them. So I can easily calculate what would be the estimated signal. So it's another experiment that, I'm supposed to read, 20 dBm, and I'm reading 10. So what's the 10 dB goal? So it'll give you a lot more additional, measurements and understanding to what we planning to do as just a first item. So anyways, anyone has any other suggestions for what we can do, we certainly apply that. It's going to benefit in multiple. We identify what the focal point is. We identify performance at 8.4 gigahertz that I've never done before in this dish. So that will give us, okay, we're capable of the GSM, and we're actually capable to detect Voyager 1. We'll just commit when we're going to do that. And as well as going to give us also the azimuthal accuracy for the dish, and also the thermal noise characteristics of the horizon, so we can swing antenna 360 degrees and actually measure. I can plot the thermal temperature. Kind of cool gonna be too. So anyways, that's what I have in my head, but there could be something else gonna be dropped in.
I was going to make a comment. I'm not sure if you're familiar with the amateur DSN group, Deep Space Network, and they routinely monitor a lot of the deep space probes. And I know even as recently as just a day or two ago, with as small as a 1.2 meter dish, they routinely can pick up at least the carrier for Juno, which is the probe that's orbiting Jupiter at this point. So a 1.2 meter dish is sufficiently for observers to actually detect the signals. So I can imagine that the DSES dish should just be a complete blasting signal for some object even like Juno out of Jupiter.
Yeah, Adrian, yeah, it's absolutely, yeah. I'm a member of amateur DSN for years. In fact, if you look at the file section on the group's I/O, you'll see a lot of software that I supplied there. So yeah, I know familiar now people, a lot of people, and a few of them actually are also our members, the SES members, like VK4 and a few others. So we're in the same environment, yeah, and those are like amateur approach where I can use my 3 meter dish here and receive all this space except Voyager because it's not going to be enough. Even though if I'm going to do integration time like minutes, it's still not going to be enough. Signal going to be buried in the noise. But Juno is totally doable. Yes, and you're right. The Juno been copied in 1.2 meter dish with the regular preamplifier, simple SDR, and what is that? Our AirSpy software. I keep forgetting what's the software name is, but just no scripts, no Python, no crap that I'm writing, calculations and all of that. Just simple. Connect to this SDR, tune to the frequency. If you off the frequency, zoom out. Oh, that Doppler shifted there, and then you see the flat on there. Boop, I'm detected. That's the minimum you can do. Anyone can do that. Anyone that has a 1+ meter dish and can be able to tune to 8.4 gigahertz and has down conversion down. I mean, certainly everyone can receive. In our case, it's going to be a lot. Of course, the signal is going to be stronger. And I already had that posted, by the way. If you look back in my initial group's I/O posting Wartness, I already had that there and estimated precisely what signal is going to be. And to everyone's surprise, some signals are 60 dB. So signal noise ratio 0, 60 dB plus 60 dB. You probably need to attenuate on the input. So yes, the signal is going to be enormous, which is good. Why? Because we know what the estimated signal is. Now we can precisely characterize the antenna, what antenna performance is. So if we're going to point and multiply deep space objects, and we know what the signal is expected to be, we know if the system copies that. If we have a common 10 dB off from everything we receive, it tells you what, we're 10 dB off. And that gives out a lot of data. I'm looking forward towards that, the more science experiments than the simple detection. I know for a fact, and there's no doubt, and I guarantee you 100%, we will detect every single DS probe that exists currently, and man-made, and put all this in the table, like a done deal. It's more like what else we can do beyond that, right? So not to get overboard. And thanks for comment. Appreciate that, Adrian. That was a good comment. Because not everyone aware that there is a very nice group, amateur DSN, a lot of postings, and like using the simple devices you have at home, like RTL and down converter with some LO and a mixer, and or if you have money, you can buy something already existed like a Kuni or down East Microwave, or build your own, and you get you to DSN. And that's a cool. I mean, if you use only dish for EME or hydrogen line, which is boring, you'll see what you see. Or unless if you're doing some drift scans or something other stuff, then you can certainly do DSN, and it's going to be a lot more interesting because it's totally different frequencies. Doppler shiftings are a lot higher than any other frequency. So anyways, anyone can go there and search for amateur-DSN and join the group and read the tons of information. I dumped some software there and posted a couple things, so anyone welcome to go there.
Yeah, well, you're welcome. It's a really interesting group. I myself am also a SARA member and have used the 20-meter greenback directed telescope dish for some astronomical observations like hydroxyl masers from detection. So yeah, there's a lot of interesting things that can be done, even with, like you said, like a really small 1.2-meter dish. So that makes it really accessible for a lot of interested amateurs. But yeah, thanks for your contribution to the amateur DSN group. That's marvelous. Thank you.
Yeah, and it's also important if we share something with others within our community. I think it's also helpful and get our name within the society. So contributing, I think, is one of the important factors. And if we successfully executed something, and with such a big dish, and once again, dish size for this particular case is it won't matter, but you can do precise things. That's what's important, and you can share with others. Others might do the same thing because some people don't understand that sometimes you don't need the big antennas to do like EME or copy June or anything like that. I had some assumption when I was in early 20s. My always stereotype assumption was that you can't do EME unless if you have a kilowatt of power, have a big stack of arrays. We're talking about like a 2-meter band, 6-meter. But that's until I tried on 5-element Yagi to do my first 3 EME QSO on 2-meter band, 5-element Yagi that I use for satellite communication, not even close to EME band, and it was successful. And then you start thinking, so it's possible if you know what you're doing. So, and that's why everyone wanted to try to do DSN. Go for it. I mean, it's doable. You don't need to wait until the sophisticated scripts are going to be existed. The reason that I created DSN simulation software called BDPDS is just if you don't understand what I have right now will work, you can actually predict everything and calculate almost precisely what you're going to get at what level. So I'll get you the reference point. Hey, I'm supposed to receive the Juno at a level of 20 dB with my 1-meter antenna. All right, shall we try? So try, you have close enough. It's already get you better motivation. So without those kind of tools, it's hard, right? You only rely that if you copy or not. So anyway, if anyone wants to have any additional, there is a whole we have on our groups.io, DSES groups.io. There is an article, a topic about PDS, and PDS software also included in the file section. Anyone can download it and use it on your computer just for simulation purposes because it's only does simulation. Anyways.
Yeah, Alex, in the interest of time, could we got a time check here? We're about an hour and a half into the meeting. Can we further the agenda here?
I'm done. I mean, Bill, there's nothing. I had only 2 topics, so it's done. I don't know what Paul has on his agenda.
Well, it's later. It's later here in Houston, so.
No, I'm just saying we got a couple more items on the agenda here.
Thank you very much, Alex. And thanks for everybody who had comments and questions. That really helped our discussion tonight. And we're moving at light speed here in terms of technical capabilities at Haswell. So got to hang on to your hats, guys, because we're getting some really neat stuff. Moving forward, let me see. The next item on our list was this last week, I was talking with Jim Schatzman, AC0XU, who's with Augustus Aerospace. and David Lindsay, who's also with them. And they proposed that they were closing down their business. They put about over $1.5 million into building it up, and they have a lot of equipment. And they said, "Would you like some of our hardware?" And so I thought, well, this is a once in a lifetime opportunity here to pick up some neat things. So I went to see what they had, and talked to Jim, and he had a 2.5 meter screen aluminum dish at his property up there in North Denver. And David Lindsay was down at the Augustus Aerospace Facilities in Centennial, and they also had a couple of 2.5 meter dishes. And also we also were able to pick up a 1.5 meter solid aluminum dish. And these dishes that we picked up came with 2.3 gigahertz feeds, of all things. So right in our sweet spot there. So I was looking for a landing spot for these things before they closed the business. They had to be at other facilities, and anything that was left over is going to go to the junkyard. So I grabbed whatever I could, and I'll show you a couple of pictures real quick here, so that way we can go through this. But the purpose of getting these things was basically outreach, learning, see if we could learn with these dishes. From what I'm hearing right now, we could probably use them for some DSN work. Some of the members may be able to borrow these dishes from the society and use them for a period of time. We could do some local testing and also some roving. There's a group going to be doing some work up on Pikes Peak I guess they're going to be trying to activate some higher bands like 10 gig and maybe 24 gig. And so that the 1.5 meter dish that we have, the solid one that we picked up, is probably a good candidate for that. So we have some great assets we just picked up. We also picked up a polar mount, which is it's a Yaesu 5500, does both azimuth and elevation, along with a green herring controller. So that's going to be a great hand. We also have some really super mounts for these dishes, so that you can put them out there and don't worry about them blowing away. They even have wheels on them. So we also picked up a 8-foot rack, which is beautiful, with some shelving, which we needed for the facility. So we had a lot of materials. We also picked up 2 flagpoles, including a Colorado flag. So we just need to get the U.S. flag, and we'll have those in our classroom coming up. Let me think, what else was I going to say here? Let me just give you a quick show, and then we can maybe just talk about the end of the EME contest and how we did.
Paul, we lost your audio and you're not sharing yet.
Come in, Houston.
Yes, Houston here. Stand by.
There we can see it.
Paul, we lost your audio again.
Okay, I found it. It's tough on a little screen like this. Man, I wish I had my 4 screens. Anyway, moving on. Can you hear me okay? Everybody good? Good. All right. Let's try this one more time here. Okay, so here's an example. This is the polar mount that I was talking about. It comes with a very strong mounting system here with a base to it, and it has wheels that move around. They were using this for radar testing at the Centennial Airport. I guess they had some radar receivers that they were working on, so they needed something to be able to test it. So this is what they were using. It has right-hand circular. This is the feed, right-hand and left-hand circular polarization. Here's a picture of a little bit of the feeds. You can kind of see there's a screen here, which is kind of hard to detect there, but this is the lighter of all the antennas that we have. And but so this is something that you would probably trot outside when the weather's good, and you can put it on the mountain and point it at whatever you need to. Here's Rick Hambley, and these are the other dishes that we picked up. The other two, that's Ray in the background there, loading it onto Rick's trailer, and it comes with some very substantial mounts that you can put them on. And obviously the feeds are not in here right now because we were trying to move it around. So we have separate feeds for those ones, and they're very, very well built feeds. So those are the pictures I have so far. Any questions on any of this? All the equipment's right now at Haswell, and one of the mounts we lent to Derek Brady, so he could maybe start working on. He wants to put up a dish at his place and try to work something, or at least see if he can try to do some EV work. So he may get one of these antennas, but we still have enough there that we can go around. But we'd like to hear from the members to see who would really be able to use these things. Another choice is also to be able to share it with the local high school if it would work into their curriculum to do some hydrogen 1420 or 1610 type of scanning. So those are the things. Any questions on any of this? Okay, that was quick. So the next, there's no questions. I'd like to just move on. I think we're probably running down low on number of people on the call right now. So Alex, you want to just give a real summary of what we found out about how we did in the contest, or what you think we did? And
yeah, I'll be quick, since last time I posted already the whatever we had results, and we also had some. If you guys subscribe to 432 newsletter, that distributed mainly through the Moon net on the Groups.io, or it's also available on the website. So there's a small article that we sent to them about our performance during the contest. So they estimated that we worked well. First of all, we worked the first time we worked a number of QSOs. I think we set the record for us. The SES is the Zero PRT participation in the EME contest by the number of total QSOs we made in a single contest. So that's the good, exciting news. And perhaps we're going to be a top 3 in the world. We're looking for the first place, but right now we don't have any estimates yet. But we did very good. And also, when I took Diane home for investigation, because we noticed that there's some power fluctuation going on with the RF signal, which happened during the first week, and appears to be that the power were lowered to about between 10 to 50 watts. So the second week of the contest, we were actually operating in the QRP mode, and was excited we made such a number of QSOs.
And also too, Alex, we had many comments afterwards, emails and things from folks who said that They were running very, very modest, small antennas, and we're the only one who was actually be able to hear them. So it was a pretty good way to do some help with them.
And also another thing, Paul, that I want to add, one of the three or five stations that worked another station that had only bow tie antenna. Would you imagine that the guy was experimenting during the contest? He was transmitting on a bow tie, double bow tie antenna, and it just basically, if anyone familiar with the bow tie, right? It's you have a plate, and then you have this bow tie that's mounted above that plate, a reflector, and that's it. He was running about 500 watts, but it's amazing because that's if you look at the directional antenna and then parabolic antenna or Yagi, you focus all your energy into such a small beam width, and that's how you get the power density. And here, your power density is absolutely not nearly close. So it's amazing that we were one of the few stations in the world that copied this guy. He was amazed by the report. We gave him the strongest report he ever copied.
Yeah, he said we're pretty strong too. So we're only running QRP, so that was pretty good time. And I also had comments from members of our club that our society that attended it, that they said they really learn a lot when they come to these things. So it's a great learning experience, classroom type experience where they can see what you can do with radio astronomy. And I think that was about the last thing I had on the agenda, except for the site. I don't know. Did you want to say anything about the site, Bill?
Yeah, let me just reiterate. We have a lot, for those that a lot of the technical information is more than you want to deal with right now as you absorb this and learn it. We have a lot of just basic work that we need done on the site. And so if you really want to contribute to the organization, the way to do that is to take on some of these projects. Most of them are infrastructure projects. Roger and I've been doing a lot of things. Paul and I've been doing a lot of things. Myron's been out there many, many times. But we have a lot of things to finish on the building, to clean up the site, get things organized, get things fixed that are, in danger of being flooded and that sort of thing. And I have this list. I don't know if I'm sharing the list or not. I can't see it.
You are.
Okay. But those things that I've done or we have done, I've marked as checked off. And those things still to come, I've marked with an A, B, or C priority just based on how I perceive those things. But we'll post this on the website and put it out there so people can pick, go through this, look at where can you contribute and what can you do to help us out to get the site organized and get it finished. And the thing about this, everybody wants to do the technical stuff. Nobody wants to do the infrastructure stuff. And yet it's the infrastructure that enables us to do all of the technical work. And so I'd like to see people pick up some of these items on this. I can't do it all. Roger can't do it all. We need help. And so take a look at all these items on this pretty large list and pick something you want to do. Let us know that you want to go to the site and we'll meet you there and get some of this stuff done. But that's all I had to say about that. We'll post this up on the website and go from there. And that's about all I got.
Hey, Bill, we talk about that with Paul. I fly there every month. I think he noticed that. Sometimes I fly twice, and I'm coming next time. It cost me only $37. Believe it or not, $37 a ticket.
That's decent.
It's cheaper than you fill the gas in your car. So say that we're talking about that you need, because I had no idea, right? I'm going there. I'd like to help more than that what I'm doing from technical, because sometimes I'm just sitting and doing nothing, and where I'm doing nothing meaning I'm just doing programming. But at that same time, I can help you out. So we're talking about installing the towers, VHF and UHF, HF towers. So right. I can take that task and do that, and other I can take Vlad with me, and we can fly sometime and do it. So So we can go through list and see what we can take it. So, but yeah, it's a good point, and I think everyone should contribute, and whether anyone do his technical job, we can also contribute to the club as well from the same place that we're going there and sleep and eat.
Yeah, and not only that, as you do this, you're learning by osmosis. You're there at this site. There's other things going on. I've got these other experiments going on. You rub elbows with Alex and learn a lot from Alex, and all of these projects that we're doing. But this is an opportunity. If you don't know what to do technically, here's some pretty simple things that are like household chores, household improvement projects, and we really need some help getting those things done.
Okay,
So that's all I got.
thank you very much. I've just got the word from the management here. We got to close down. But thank you very much, everybody. And Bill, if you could post that on the groups IO and put it in the files section for everybody as well, so they can pull down the list easily and then they can print it out. That would be a great help. Okay.
Okay.
Thank you, guys. Have a good evening, everybody, and thanks again for joining the Deep Space Exploration Society tonight.
Good night. Thank you.
All right. Good night.
All right.